Rule of 3 is this is the rule of 3. So when p is very small, you may not observe it's happening within the sample. So what it means is the occurring probability proportion is like a 0.2% happening, which means is if you try 1000 times, you will observe 2 times, right? So 0.2% means is 2 times out of 1000. So if you collect the like a 100 200 sample, maybe you may not see any of the observation, right? So that case we can use the rule of 3. If in an independent trial no event occurs, this is possible when p is small, then the upper 95% confidence bound is approximately by the 3 divided by n. For example, if the no medical complication arises in the 17th surgery, the upper bound, I don't know what will be the p here, or what will be the pi here, because I don't see the medical complication in 17 trial. So maybe this is like 1% or very small chance to happen, but I cannot observe anything, so how can I estimate it? So I don't know what will be the p or what will be the pi, but the upper bound. But I can tell this should be less than 3 divided by n. So if you divide 3 divided by 17, you will get a 0.18, which means the proportion of medical complication will be less than 18%. Okay. So this rule is used when the limited data is available. So when you can observe data a lot, then you can just simply increase the number of n. Then maybe you can observe the 1 or 2 medical complication. Then you can estimate p, pi, and so on. But when you cannot have a lot of data, then you can use this kind of upper limit. I don't know what is the number, but it will be less than certain proportion. And the rule of 3 is a conservative approach. Okay, if sample size n is less than 5% of population, we can consider we are sampling without replacement. We can consider the population is large enough. So n is smaller than 5% of population, then population is large enough, so we can consider that an infinite population. So every time we selected a new sample, actually the proportion of happening or not will not affected by the what kind of member was selected as a sample in before, because there are so many population, so the probability or the selecting will not affected by what happened in the previous. However, if you selected a sample relatively a lot, greater than 5%, then your interval actually less than what the sample size is, because you are collecting significant number of member of population. Then you can tighten your confidence interval. So in that case, we can little bit tune the confidence interval, because you are collecting relatively large size of sample. So we will just adjust our confidence interval in that case when the population can be considered finite, which means n is greater than 5% of population. In that case, we will tune our confidence interval using this finite population correction factor. This is the one. So n minus n divided by n minus 1 and square root. So if you think about it, large n is really greater than the smaller n. This will be just 1, right? So for example, I will give you the 10 million minus 100 divided by 10 million minus 1. This will be almost 1, right? If you take out 10 million minus 100, that is pretty close to the 10 million, right? And 10 million minus 1 is also pretty close to 10 million. So the calculation will be just 1. So this is the case, n is the large n is a lot larger than the n. However, this sample size n, small n, is a significant amount of the population. Then this will not be 1. So you should correct your confidence interval because your sample size is significantly large. Then you can have a little more confidence. So we can just simply multiply to our margin of error here, the same way here. However, our textbook has some kind of typo. In the textbook, you might see this kind of formula, right? N minus n, n minus 1. Okay. However, this is not the right one. Okay. So you may see this something like this, but this is wrong. This is not the right one. This is correct one. This is correct. If you take a look at the formula for the 8.15 in the textbook, you might see the square root has this kind of form. This is wrong. This is correct one. Okay, you just simply, that's easier, right? You just simply multiply the finite population correction factor when n is greater than 5% of n. Right? There is a 1000 employee and randomly sample the 75 employee, and then they're just trying to measure what is the average number of hours per week the on-site exercise facility. So kind of ZIM. So you can find out the sample mean is 3.5 hours per week, and that's standard deviation. And then we can calculate the confidence interval, which will be since we don't know the standard deviation, we have to use a t. I don't know what confidence level you want, but actually you can do, this is 75. However, 75 is more than 5% of 1000. 75 is 7.5%. So this is, you have to consider this effect, which is 1000 minus 75 over 1000 minus 1. Then you can create the confidence interval of the average number of hours per week the employee use on site the exercise facility. So you just calculating this way, and then you can find out the confidence interval. If we don't correct this finite population correction factor, then you will have a little wider, as you can see here. If we don't use this factor, your confidence interval is a little wider. So actually, if you use this finite population correction factor, your interval getting tighter, smaller. This is like opposite calculation. When you want to know how many sample size, how many sample do I have to collect, if you have a certain maximum allowable margin of error, E. So here the margin of error, E, is Z times sigma over square root of n. But how usually we find out Z, and we got a sigma and we got n, and we calculate the E. However, if the E is given, if this is a desired if there is a desired E, how can I calculate the n? But actually it looks like the new formula, but this formula can be, if you just solve for n, you can get this formula. I will multiply square root of n both sides, right? Then it will be square root of n E Z times sigma, right? And then I am dividing E both sides, and square root of n will be Z times sigma divided by E, and then I am taking square root of square both sides, then it will be Z times sigma over E square. That is this formula. So this is not the brand new one. Actually, we already used this one so far. We just calculate. Previously n is given and we calculate E. Now if E is given, then we can calculate n. So now when we're trying to find out the sample size, our formula was n equals Z times sigma over E square. So let's say E is the given number, we have a desired margin of error, and then Z will be the given by our confidence level. Now how can I find out the sigma when we decide n? So method 1 is you can just do the preliminary sample. So you just collect a little sample and then estimate S and for the sigma, and then you can plug in here, and then you can find the sample size for the real sample. Or second one is we assume the uniform distribution. Uniform distribution doesn't have a center. Most of the case, this is the normal distribution. The center is the thickest part. However, the uniform is there is no center concentration at all. So if you use a normal distribution, and then if you calculate the standard deviation, this standard deviation is actually relatively big. So if you use a big standard deviation, means you are calculating n a lot. So this is a very conservative way, because uniform distribution is a relatively high standard deviation. High standard deviation requires more number of sample, so larger number of n. So this is the conservative way. So I'm just choosing which is a pretty worst case, and then preparing the sample size. Assuming normal distribution, because normal distribution is the most popular one. So how can I find the sigma here? Is using biggest number minus smallest number divided by 6. Where this formula comes from is the normal distribution. We already know 99% of them will fall in between plus minus 3 sigma, right? So which means is from here is 3 sigma, this side is 3 sigma. So from here to here will be in total 6 sigma. So if you have a lower bound and upper bound, that should be the length of this range should be the 6 sigma. So you can just divide by 6 both sides and you can get a biggest number and the smallest number. Divide by 6 will be the sigma. That's a rough estimation. And then you can use this sigma plug in here and then you can calculate the n. Or the other one is some special case. You can use a Poisson. You can assume the Poisson. Then you can do this, but that's kind of a special case.